What I'd like to talk to you about for the next few minutes is about Hurricane Joaquin and how it influenced San Salvador Island. It turns out that Hurricane Joaquin did more severe damage to other islands. San Salvador was relatively unharmed. There were structural damage, but in the grand scheme of things, they dodged a bullet. However, what happened on San Salvador in terms of the variety of damage that was caused, I think serves as a good sort of lesson learned and instructive way, if you will, to how the Bahamas can manage storm impacts in the future. So if I could be so bold, I would like to look at San Salvador and see what lessons can be learned in the way in which the Bahamas can then manage damage impact in the future. Lisa went over some of the demographics of San Joaquin's effects in the Bahamas. I'm not going to spend any time on this except to say, of these demographic characteristics, the one that has the greatest potential impact geologically, the one effect that can influence the coast and its geomorphology, is by far storm surge. Storm surge wasn't directly measured anywhere in the Bahamas, but there are indications that on Rumkey, Crooked, Acklins, and in San Salvador, at least in certain regions around those islands, the storm surge was as much as 15 feet. This just shows the track of Hurricane Joaquin. It kind of danced around a little bit for those first 3 days in October. And in essence, I think that's what exacerbated the effects on those southern and central islands. In terms of damage, in terms of infrastructural damage, the one part of the island that showed complete structural loss was the southern shore, particularly near the southeast. This photograph here shows what was left of a home on that southeast corner there on the southern shore. It turns out that this was essentially the only place on the island where there was intense and complete structural loss, and that structural loss is principally caused by the storm surge that was experienced here on the south side. Elsewhere on the island, as Lisa has shown, there was lots of lesser structural damage, particularly to roofs and interior of homes, and that was essentially caused by wind-related damage. So most of the island was influenced by wind effects rather than surge effects. The kinds of questions we want to ask, the kind of questions that I and Lisa and our co-authors would argue that are important to the Bahamas are as follows, okay? What kinds of coastal geomorphological change is occurring when storms strike? In other words, Joaquin has hit San Salvador Island along with other islands in the Bahamas. Are there permanent effects to the geomorphology as a consequence of that storm? That should be a first consideration when managing storm impact in the nation. How does it vary geographically? Okay, again, storms are kind of specific. They're not hitting everywhere. Certain areas are affected more than others. So what this analysis does is it looks at how that damage varied around the island of the Bahamas. Again, around San Salvador. Again, to give you a sense of how variable damage can be and how variable risk can be or vulnerability can be around the islands. Third. I want to look a little bit at the severity of the coastal erosion and deposition on San Salvador that was caused by Joaquin, and was that impactful enough to cause a permanent geomorphological change? It turns out that there were at least a couple of places where this turns out to be true. And then last but not least, how can the assessment here of Joaquin's influence on San Salvador help the Bahamas address coastal vulnerability in an ultimate sense? So at the end of this talk, I'm going to suggest a mechanism that could be used, that can be lessened from this study. What I want to introduce to you is it's a conceptual model that's been used by the U.S. Geological Survey in the United States. It was developed by a geologist named Salinger in 2000. It's known as the Storm Impact and Vulnerability Conceptual Model. And essentially what it does is it looks at two principal variables that influence vulnerability in coastal regions. Okay? The first is how high the barrier, or in the case for most Bahamian islands, the foredune happens to be. How high is the highest portion of the dune? How low is the lowest portion of the dune? And that varies as you move from one spot to another. The second influential factor is known as swash height, or the R value. Okay? Swash height is how far up the beach the the storm influence rises, and swash height is really a function of the tidal surge that's caused by the storm itself. It's also influenced by wave height and wave run-up. And so that height of swash can be high and it can be low. The way this vulnerability assessment works is it compares the D and the R values for different geographic locations in your region of interest. In essence, then, there are 4 levels of impact that can be defined using these 2 variables. And you can see them here from left to right. Swash damage is when the lowest part of the dune is higher than the highest swash. Okay, so the water gets up the beach, but it doesn't impact the dune at all. And we call that swash damage. And that's the kind of damage that's ephemeral. That's the kind of damage that can happen every day. That's the kind of damage that an environment can repair naturally over the short term. If that R high value is great enough to influence at least the lower portion of the dune, but not be higher than the highest portion of the dune, you get what's known as collision damage. And in essence, you do damage to the barrier. You reduce its capacity to withstand impacts of future storms, but your structure is still there and doing the job it was intended to do. And in essence, what happens in these situations is the dune is eroded or the dune is scarped. If the swash high value is higher than the dune itself, well, then things change drastically, and you start to see very influential and permanent changes to the coastal geomorphology. In the overwash mode, the waves are actually breaking over the structure, okay, and actually moving sand from up in front to behind, shifting the dune's structure and position. And then the worst situation entirely is when the lowest value of the swash there at the lowest tides is actually higher than the highest portion of the dune, and then you have an inundation situation, which means all hell is broken loose and your coast is drastically influenced in a permanent way. So what I'm going to do is I'm going to take you on a tour of San Salvador Island and show you where and why these kinds of impacts have occurred. The methods that we're employing, we did this assessment with our team for a week. It was a quick trip in the middle of January. We actually focused on 9 study regions around the island. We selected them to provide a variety of settings and geographies. We did aerial surveys using drones. We were using a very sophisticated technology to actually generate orthophotos and digital elevation maps, so our imagery is quite useful and spectacular. We did ground-based surveys, which means making observations on the ground, actually doing beach profiling and looking at the shape and shape of the beaches and the damage the storm created. We also did ground-penetrating radar work to look at how the storm influenced what we're able to see in the subsurface. And then Lisa talked to you a little bit about the tempestology work that she's done, and we cored a few ponds that experienced overwash. I'm not going to report any information from these last 2, the GPR and the coring work, and just focus on the aerial surveys and the ground-based surveys. Here is the island of San Salvador. If you're not sure where it is, it's kind of hanging out there on the eastern edge of the central Bahamas. This is a close-up of the island itself. The red ovals represent the 9 surveyed regions that we studied, and the ones that are in yellow are the ones I'm going to share with you today. So I'm going to take you on a quick field trip, if you will. I'm going to first show you the Gulf here on the southern shore of the island, then Salt Pond Beach on the windward and east side of the island, and then Ferdinandez Bay on the leeward and west side of the island. Okay, first the Gulf. The Gulf was an area where the surge was the highest, so the R values were quite high here, okay? And this is a part of the coast that experienced both overwash and inundation impact. One of the inundation impacts was the production of this boulder field. So this region that you see here are actually boulders that were thrown up onto this 5-meter high cliff, limestone cliff, to create a boulder field. And then a little further to the east, where you lose the outcrop and you start seeing sandy beach, this is an area that experienced overwash. So everything that you see here and everything you see here is new as of Hurricane Joaquin. This image shows another portion of that region. The colors aren't coming out very well, but let me point out the highlights here. This particular region, sitting on top of the 5-meter high cliffs, is a place where boulders were literally plucked by the storm. All those white scars are places where material was removed. And those boulders that were plucked were then deposited here in areas 3 and 4. Okay? And back here in area 6, this is an area that didn't experience boulder deposition, but it's an area that experience death of the vegetation because of saltwater inundation. This is like the ultimate in narcissism. This is a selfie taken from a drone. So if you're looking for new ways to take pictures of yourself for your Facebook page, this is a good way to do it. So we're actually controlling the drone here while we're sitting on a Joaquin deposited boulder and having that photograph taken. And what you're seeing here is the boulder field. All of these materials stretching as far as the eye can see essentially represent boulders that were plucked either out of the subtidal or off of this portion of the cliff face and deposited behind it. This is a photograph showing you what the plucked areas look like. This is one of our friends and colleagues who's standing on an area where you can see fresh outcrops. These rocks are milky white simply because they were literally just stripped clean and those boulders were removed. And then behind it, a little further to the north, you can see the boulders being piled up on the landscape. This is perhaps one of the most interesting and compelling images to express just how bizarre this situation is. This is the same spot photographed in 2012 on the left and 2016 when we were there in January. And you can see the person on the left is standing on boulders from a previous storm. So this is a region that has experienced inundation and boulder deposition multiple times. Here on the right, all those boulders have been picked up and moved further to the right as a consequence of Hurricane Joaquin. A subset of our group actually did a boulder analysis in 2012, and they had the foresight enough to actually identify 12 boulders, okay, characterize them, photograph them, and locate them. Okay, you can see the data here, the sizes of the boulders, their volumes, and their estimated masses. So you've got boulders here that are up to 4,500 kilograms in mass. And then this column that's colored shows the disposition of those boulders as a consequence of Hurricane Joaquin. And what you can see here is that there are a lot of boulders that are just missing. Either we couldn't find them because they weren't located well originally, or more than likely they've been picked up and moved so extremely that we were unable to locate them. And then there are lots of other boulders here that are moved as much as 26 meters. So we're talking about quite an intense force that's capable of influencing this part of the coast. If you move a little bit further to the east of that boulder region, this is where you've got the production of this overwash fan. So what you're seeing in this photograph, here's where the outcrops end and the sandy beach begins. This is a surge channel that was created by the storm, and this fan is sediment that was deposited as a consequence of Joaquin. Again, something that wasn't there prior to the storm. We did a quick survey of that fan. It turns out to be about 10,000 square meters in size, a hectare, and contains about 11,000 cubic meters of sand. So it's a significant amount of material that's been moved by the storm. And again, this is material that's moved that isn't going to move back. It's there in perpetuity. There's no mechanism to take that sand and stick it back from where it came when you're dealing with inundation and overwash damage. Let me take you to Salt Pond Beach on the east shore. This is an area that experienced overwash impact to the north and collision impact to the south. If I advance, I can show you a little bit of the landscape here. Up here, the dune ridge is quite shallow. So the dune height is low. Because the dune height is low, the surge was able to overtop the dune here. Down here, the dune climbs to appreciable height. So overwash didn't occur. The dune did its job, and it was eroded and scarped, but it didn't allow material to bypass it. Interestingly, a human impact, if you will, the Fortune Hill Cemetery sits down here. The Fortune Hill Cemetery is a cemetery that's been in existence since plantation era times, and that area experienced severe erosion as a consequence of the storm as well. In fact, this is a picture of the Fortune Hill Cemetery. The original edge of the cemetery and the edge of the dune sits out here. You can see the concrete slabs that represented the original wall. This is the setback as a consequence of collision damage, a setback of almost 3 meters. So there's a significant amount of the dune that's lost here, but the dune at least is still there to do its job. We're lucky to have had historical beach profiles taken of a number of areas throughout San Salvador Island. So we're able to compare what the beach profiles look like then with what they look like now. These are 2 profiles, one taken in June in 2014, and then the same profile taken after Joaquin this past January. And this is an area where the dune ridge is low and overwash occurred. Just to quickly point out, the water is to the left, the inland part of the island is to the right. You actually can see a shift, a lowering of the height of the dune between here and here. This dune is actually lower in height, in absolute height, than this one is. They're not to the same scale, but this dune has actually been pushed back as much as 4 meters, and all of this material here that you can see isn't as voluminous as it is back here, is overwash that was moved by the storm. If you do the same kind of thing, but now further to the south, where the dune ridge is higher, okay, here you're not seeing overwash damage, but rather you're seeing just collision damage. Here's the dune in 2014. It's significantly higher than the dune you saw on the previous slide, and then this material, all located under here, has been eroded to create this new dune scarp as a consequence of Joaquin. And again, the distance that this dune has moved back or been eroded back is about 2.75 meters. So again, significant collision damage, but at least here, this is ultimately repairable. The dune can repair itself given the transition of enough time. I wanted to, how much time do I really have? 2 minutes? I'm gonna skip this. I'm gonna skip this, or I'm gonna go over it quickly. I think what I'll do is, this is the east side, or excuse me, the west side of the area, Fernandez Beach, where a seawall exists, okay? And this seawall was actually fortified in 2014. Okay, the seawall was actually made higher. That's the original height of the seawall. That's the new height of the seawall. I don't have time to explain to you how we lucked into this data set, but suffice it to say, because of the construction of the dune, we were able to assess how much beach was eroded since the passage, or by the passage of Hurricane Joaquin, and that's what's shown by this graph. So this is a 100-meter transect that runs along from north to south along the base of the seawall, and the area underneath this curve represents the amount of sand swash damage that was caused by Joaquin, and that totals something like almost 64 square meters, at least in cross-sectional area, along this 100-meter transect. So that's a lot of sand that's been removed, okay? But again, this is swash damage. That sand will come back. That sand hasn't been thrown over the wall and moved to some other part of the island where it's not accessible in the future. Okay, so let me come down to the important parts. First, let me assess for you or summarize the coastal effects here in San Salvador. San Salvador experienced sustained, significant swash and collision impact. The two types of impacts that are most readily dealt with because they are naturally repairable. Okay? The swash damage occurred everywhere along the island, but again, it's repairing as we speak. Those sands are coming in or coming back on a day-to-day basis. The collision damage, the dune scarping, the erosion of the dunes, was most significant on the eastern shore and in that southeastern corner. These are serious impacts, but given enough time, assuming those dunes aren't damaged anymore in the near future, they too will be repaired. Overwash damage was greatest along the south shore, east of the Gulf. This is where that large washover fan sits. That washover fan is now part of the landscape. It's not going away unless it's removed by human activity. And then the inundation damage that occurred along the southern shore at the Gulf, that is indeed an inundation damage. The good news there is that inundation occurred over a well-cemented, lithified ridge. Okay, so it didn't erode away like an inundation effect would have on an area that just had a non-lithified, a non-cemented dune. So the Gulf, fortunately for the Gulf, it was armored by the limestone that sits or outcrops in that area. In terms of grand implications for San Salvador, storm vulnerability is influenced again both by dune height and swash height. And both of these vary considerably around the island, and they vary considerably around the entirety of the Bahamas. Okay? The South Shore is a part of San Salvador where the platform, the shallow water area, is very, very narrow. So that's an area that's always going to have high R values if a storm sets up a particular way. There are plenty of places in the Bahamas where the coastline is inhabited by society, where that platform is very narrow, and they're likely to experience very high I values. The dune height is lower on the leeward side and on the leeward westward side, but this is an area, even though the dune is high, where swash R values can be quite high depending upon storm setup in the future. Okay? And then dune height is appreciably higher on the north and east coasts. There are smaller communities here, but again, communities that could be influenced by those kinds of impacts. Okay, I know I'm out of time, but this is probably the most important thing we have to share for you. The recommendations for the Commonwealth. The Bahamas really needs to know what its D and R values are everywhere. The D values require that there be elevation surveys done, at the very least, of all the coastal perimeters. And the best way to do that is by using LIDAR and GIS technology. The technology exists. It's relatively inexpensive, depending upon your point of view, but you can get a lot of information about elevations very, very quickly. You'd get your D values for a relatively small investment. In addition, the Bahamas has storm surge modeling, but those models date back to the 1990s. Models are much more sophisticated now. They can be done at a smaller spatial level. It would be really great if the Bahamas had better information about what kinds of swash heights might exist. And then to tie this back to climate change, storms are going to become more intense, perhaps more frequent, and sea level rise is going to, in effect, increase the R value as we move into the future. This really needs to be done with sea level rise in mind. And again, I know I'm really, really out of time. I need to show you this one image. Lisa's my friend. She'll hurt me later, and that's okay. This is essentially what the U.S. Geological Survey does in anticipation of a storm. This is modeling swash height models that were run for Hurricane Sandy prior to the arrival of Hurricane Sandy in 2012, and they were able to tell the communities, because they had the dune heights in advance, they were able to tell the communities where the risks of overwash and inundation were most likely to occur. And obviously those are the places where you want to save people's lives and manage things accordingly. Thank you.